So now in this video, we're going to look at how you can take a couple of NAND gates, not and then make it an AND gate. So with the AND gate, we're going to get the electrical properties that we see with this circuit. Although there is no actual AND gate built into this integrated circuit. We have two low inputs right there. Output is low. If one goes high, it doesn't matter. Output stays low because we have at least one low input. If we turn this one high, again, doesn't matter. That one's low, so the output is low. Only time the output is high, and I should actually make sure I discharge any built up static electricity before I pull up. This one's floating now. It's actually bouncing back and forth due to stray signals in the air. And if I touch this, my body actually can like pull down the voltage a bit. If I let go though, and like touch it again, it's different each time. So you can tell it's like storing a charge. But in case, static electricity from my body can, fry gates and stuff in the transistors. So you want to definitely discharge yourself. Some people leave a band on their wrist at all times where it keeps their body grounded at all times. So that's the best option, but I don't want to go through all that effort. Now we have both inputs high, outputs high. That's the main thing. This one, we don't have the stray signals, so it's not getting a high and low voltage like this one over here was. Instead, we actually have like a middle ground voltage, and it looks like we can actually get a middle ground voltage coming out of these integrated circuits. These are not Schmitt trigger. Schmitt trigger versions, we would not get this. It would go solid to high or low, and then a middle ground region where it could be either one. But once it switches, it wants to stay in that spot until you overcome hysteresis. Then it switches the other. It wants to stay that until you overcome the hysteresis. We're not going to worry about that now. Just wanted to point that out. Try to always point that out. So I like to see what happens if you go to middle ground regions with all integrated circuits I work with. So there we go. We have at least one low input. Output is low. But we can set it to our starting position again. We have NAND gates now. So they have the opposite. We just saw this circuit. Both inputs have to be high for the output to be high. For the NAND gate though, both inputs have to be high for the output to be low. So in this case, the output will be high, even though the inputs are to the negative spot. If I flip one or the other, it's going to stay high. It doesn't matter. They both have to go high, and then they'll go low. But we take the output of that one and another NAND gate. If you tie their inputs together, now there's only two states that this one can see. That one can never be high while that one's low, and this one can never be high while that one's low. They're either both high or they are both low right there. So we now have a NOT gate with one of these NAND gates. Very easy to make a NOT gate. Just tie their inputs together. So whatever we give to this one will be inverted. So with the AND gate, you need both inputs high, which will make this low, but the low inputs will make that high. So too high in will be too high out. If both of these, or even just one of these, doesn't matter, is low. So there's three positions where one will be low or both will be low. Then the output will be high, but this inverts that to low. So if at least one of this is low or both low, this is going to be low. That's the AND gate. So now, even though the circuit's made up of two NAND gates, you don't worry about that. We combine them now. They are an AND gate. Just like there's transistors. There's no NAND gate transistor. There's transistors that are put together to make a NAND gate in the integrated circuit. You don't care about that. You just care, you may care about the properties of them for, how it affects your circuit otherwise. But as a logic gate, all you really care about is that there's a NAND gate there, a NAND gate there, there, and there. There's four NAND gates. When you combine two of them, now it's an AND gate as far as the circuit's concerned. Even though there's NAND gates built into the integrated circuit. Now, the two that we combined are an AND gate. That's all we care about. So that's the truth table you look at now, And so hopefully that makes sense. Both inputs low, negative supply, most of the way to ground, 0 volts. you got a low out. Same as if there's just one or the other one. You know, as long as at least one of them is low. Every single input, some integrated circuits have more than 2 inputs. They have 3 or 4 or whatever. Then as long as all of them though are high, close to 5 volts, the output will be as close to 5 volts as it can get. I don't know the limitation right there. But we saw that this particular integrated circuit can power up to 25 milliamps of current at each output. If you're powering with all 4 outputs, you want to limit it to a maximum of 50 milliamps of current. That's either a sink in or source. So you'd have to cut that in half. But as long as you're only using 2 of them, the 2 of them can power up to 25 milliamps of current. So I don't think the voltage is getting thrown way off here, but I could be wrong. I don't remember the limitations. Obviously, it's enough to light LEDs. So it makes for a good LED demonstration circuit right there. Need 2 high inputs for a high out. Now, even though each one of these needs to have 2 high inputs for a low. So you can see we got that output there. Input, input, output. Now that output is going to the input of that NAND gate, and the other input is tied directly to that input. The 2 inputs are tied directly together. So this is all one connection now. All these 3 rows right there. See, exact same. It's called a node. They're all the 3 together. They all have the same voltage across them, whether it's providing or looking at that voltage. So that's how we wire it up. And then I got a jumper here going to the output. All I had to do from the last video is remove the 2 jumpers that were going to unused inputs, because we're starting to use them now. Output to input, output to input. And then I moved this jumper, which was coming from that NAND gate to power the load. I just had to go to this output right there. It just took, you know, maybe like 10-20 seconds to rewire this from one NAND gate to a couple of NAND gates, making an AND gate. So that's why the NAND gate integrated circuits are the most common ones. You could use NOR too, but people prefer NAND for whatever reason. And so, you know, that's the most common integrated circuit. You'll see it a lot in like schematics. If you look at them, sometimes you'll see them combined like this, and that is why. Maybe you need a NAND gate in part of a circuit, and then you need an AND gate somewhere else. You have those unused NANDs. You can just turn into an AND, and now they're being used. And maybe you also need a NOT gate. You could just make that one a NOT gate. Then you could have 3 different logic gates out of the 4 on there, because you need to combine a couple of them. But in case rambled on long enough, hope you enjoyed. Make sure you check out one of the other videos I'm posting on the screen, and check out the links down below. They all help out a lot. I'll see you in the next video.